floor is yours.
Thank you, Laetitia. Bonjour à tous et à toutes. Merci, Diego. Merci à vous de nous recevoir ici aujourd'hui. My name is Eduardo, as Laetitia already said. I'm going to switch to English because I think there might also be some people watching us online who don't speak French. But if you prefer to speak French, please feel free to talk to me in French. I am learning, practicing would be good for me. So thank you. So as Laetitia said, I work for Gamble Technologies, which is a Canadian company. Luca's with Ametek, and today we're going to talk to you about electrochemical impedance. But just to give you a quick overview of what our company is. So we're Gamble Technologies Limited, or GTL. We are a distribution company here in Canada, and we have products for different segments. So we have nuclear analysis and radiation measurements, materials characterization and electrochemistry, optical spectroscopy and imaging, and CBRNE solutions. This is more geared towards homeland security. Our company has offices across Canada. So we have an office in Vancouver, Calgary. Our headquarters are in Mississauga. That's where our service team is as well. And I am based in Kingston/Ottawa. So I would be the closest representative to your region. So if you have any questions, please feel free to contact me directly. So just telling you a little bit more about our products. For electrochemistry, we work with Princeton Applied Research, or PAR, and also with Solartron. So we can provide you single channel potential stats with EIS capability, current boosters, low current modules, multi-channel potential stats. We have battery analyzers. This is a very new product we have that is very interesting. Electrochemical accessories, cells, electrodes, a lot of things. So if you have any needs for your electrochemical experiments, feel free to send me a note and we can discuss this as well here after this seminar. I just wanted to show you quickly some of our other suppliers to give you an idea. So here I have Ocean Insight. They do modular spectrometers, so they're very small. They can fit like in your hand, and you can do lots of different stuff with these systems. The one I have in the picture here is for Raman measurements. And then the other one that I have there is Vision Analytical. This one, they developed this product that is able to assist you in analyzing the size and the morphology of your particles. We have many other suppliers, many other products. So if you have other experiments that you're planning to do, feel free to ask us some questions. Maybe we can work together and help you with some solutions. So now enough about GTL. I want to get back to today's seminar. So today I bring you my colleague, Luca Pini, who is going to talk to you about electrochemical impedance, how to manage and interpret the results in different applications. So Luca, he comes from Italy. He's been working on electrochemistry for more than 25 years already. So he has a lot of experience and he knows a lot about different techniques. And Luca has been working at Ametek since 2015, right? Since 2015. And he is the territory manager for Africa, Middle East, the Caribbean, Latin America, and since last year, he's been in charge of Canada as well. This is Luca's first visit to Canada. He speaks many different languages, very accessible person, and I know he's very excited to talk to you about impedance. So with this, I want to pass the word to Luca now, and thank you, Luca.
Oh, yeah.
Oh, you have your own now. All right, thank you, everyone.
Sorry, without mask is better. You see my mouth, you may see my face. Bonjour à tous, bonjour. Je suis très heureuse. I am very happy to be here and thank you very much for this occasion. It's my first in-person visit after 18 months. So I'm excited like a kid. So I'm sorry, but it's really wonderful to be with real customer, real people after such a long time. My presentation, my idea to introduce the electrochemical impedance is based on what is the normal request when the people are using impedance, because everyone like to use impedance. In the last years, there is a lot of people working with impedance, but then the main issues is after the measurements, what I can do with the data. So I see a wonderful plot and I said, and now? How I understand what there is behind. So my idea is today give you some, of course, I will not open completely the door about the knowledge, but I give you some tricks, some tips, how to manage the data and how to handle the impedance data in the way they become more useful or more clear, and you can analyze better the information. So, first of all, we will see why electrochemical impedance, why the impedance is very important. We will go through some slides. I promise you it will be only few slides about the theory. I will not torture with the theory that if you like, there are a huge, nice 1,000 plus books about the theory. I will not torture on the theory, but we will go through the cell setup, so how you can connect your setup, and then some electrical circuit review and some rules how to handle the data and how to handle your experiment. Because it's fundamental how to manage your experiment to get the proper data at the end. Then we will show about some instrumentation, because depending what you want to do it, you can use one equipment or another equipment. And then we will try to get some final conclusion about the impedance. The timing, I will torture you. I will try to be as fast as possible, but of course you can stop me always and say, Luca, it's not clear. And I'm happy that I have a wonderful and large board that I can fill up with a lot of circuits. Okay, so let's starting with why electrochemical impedance spectroscopy. As you know, there is a large number of methods on electrochemistry. You have always the DC techniques like cycle voltammetry, chronoamperometry, chronopotentiometry, and then whenever you go on DC measurements, you have also the alternative that is AC measurements. So electrochemical method with AC apply. Let's go one by one. So the DC methods, it's really clear to analyze. You see this very nice cycle voltammetry. I call the cycle voltammetry the mother of all the electrochemical people. So whenever you manage electrochemistry, you suffer with the cycle voltammetry. You have your redox reaction, your iron, you come from iron 2 to iron 3, you become back to iron 3 from iron 2, you have your peak, you have a cycle, and it's very easy to recognize your system, your measurements. But where are the problem? The problem, first of all, is that your system is driving far from equilibrium. You modify your system, so you pass from one potential to another potential, and you mainly come back. So when you have this variation, you modify your surface, you modify something happening in your system. So what you have at the beginning, at time zero, after your cycle voltammetry, is not anymore the same. You modify something. And sometimes you don't want to apply this modification, you don't want to change the style. So the first problem you face is that this modification. And then you also miss some information that are very important about the dynamic of the system. You don't know all the thermodynamics response of what's going on your cycle voltammetry. You don't know, for example, some other reaction that are taking care, or some diffusion information that are behind this, and it's very difficult to get it. So the DC method is very nice, very useful, but you miss something. Let's think in this way. This is a typical dummy cell that is in circuits where you have a resistance, you have a resistance and double layer capacitance, you have another resistance and double layer capacitance. After we will analyze exactly what's going on this setup, but let's think in this way. You have all the value of your resistance 1, 2, 3, the two capacitor value. If you do a cycle voltammetry, you receive this signal. This signal it's an interesting line. Well, from this line, you can using the Ohm law for catching the linear regression. You make the slope, 1 divide the slope, and from this value, you get the value of the total resistance. So the slope, the 1 divide the slope, it's equal 7,021.98. If you calculate, we are very close to the results of the three resistance. But I don't know if it's R1, R2, or R3. I have the total. And I don't know the value of the two capacitors. If I'm doing the same with impedance, I will see something like this. This is a plot called Nyquist. In this plot, I can figure out that I have the first point. Let me getting this. Okay. The battery is very off. It's 18 months without using, the battery is gone. Okay, but you have a two semicircle. The first semicircle points in the lower part. In this point, you have the first resistance. In these points, you have the first resistance minus these values, you have the second resistance. And in these points, you have the first value minus this one, you have the third resistance. So you can calculate all the value in one single. There is a laser. Oh, shit. No, you cannot see the. Okay, so this is the three resistance, but not only. I can do also from this calculation where I have my top points of the two semicircle, I can also analyze at the two value, the two capacitance. So in one single shot, I can analyze the complete overview of my electrochemical circuits. Now you can see how is interesting the difference between the DC techniques and the impedance techniques. I'm not finished, I have some slides more. So, the big advantage, first advantage, the system remain at equilibrium. I not change my potential. I apply a very small potential, and 90% of the time is the open circuit potential. The method is not destructive, so I'm not changing the potential, the things not change. So I can reuse my sample how many times I like it. And can be applied in different fields. I can use the impedance for corrosion, biosensor, solar cell, semiconductor, supercapacitor. There are a lot of applications for impedance. I will show you some example later because they will help me for explain all the elements. But what the hell is the electrochemical impedance? Is a study of variation of the impedance for electrochemical system with a frequency of a small amplitude AC perturbation. This is the UPAC definition, so it's the Bible. So this is the definition you have for the impedance. The variation is small. There will be some application, we will see later that there are some applications where you apply a large amplitude, but normally it's very small amplitude. Ready for the theory? Question about the introduction?
I have one.
Yes.
When you said it's non-destructive, because when you finish our test, IES test, normally we can see the region that we happen to say that we tested the samples, like we can see like a circle. So really non-destructive or?
Depends to how much small amplitude you apply and depends to which potential you apply. If you apply what is called the open circuit potential, that is the potential of the cell, you still not see any modification. You should not see any modification if the amplitude is very small. Because the amplitude is normally 10 millivolts, and a variation of 10 millivolts should not modify your system. If you see any modification with 10 millivolts, then you can use a smaller amplitude eventually, because probably you are in a condition that this small amplitude will also give a problem. So the values are flexible. But normally, if you are working at what we call open circuit potential, the open circuit potential is the natural potential of your cell. Nothing should change. Should. Okay, so let's go for the theory. The base of everything is the Ohm law. I believe that if you are here, everyone knows the Ohm law. Otherwise, please, you are welcome to take a nice book about the Ohm law and read about. But I believe that everyone knows about the Ohm law. So the resistance is equal potential divided current. And this is very correct when we are in DC system. When we are in AC system, the impedance is a transfer function between potential and current, but we have something in between that is a sinusoidal signal, because our signal is not anymore direct, but is going up and down following our AC system. So we apply an AC potential and we measure an AC current. Now, this system should be very small, because depending if it's small, if larger it is, you can see from here, if I apply a larger setup in this point, I will have a larger signal to the other. So larger is the potential, larger will be the current, depending to how is the dependency of this value. No, sorry. But I believe there is. It should be spotlights, should be this. No. This one. But you can.
I can see that.
Yes. No. People online, they can see it, but not everyone.
Okay. Yes, maybe it's just the time. Can you see online also? No. Okay.
For online, look at the video. If you see on the video, they see online.
No, we don't see. She put the pointer here, but we don't see.
Yes.
Okay.
No. Okay. I'm sorry.
I'm sorry. Okay, so the response will be measured to the other side like this. Okay, let's close this part. Then another point that we have in our system is that we have what is called a phase angle. So the variation between the potential and the current has inside also a value that is the phase angle. What is the phase angle? The phase angle is whenever I apply a potential, the delay on the response from the current is marked in phase angle. So sometimes current and potential start at the same points and finish at the same points. So we say that in this case, we are in phase. When I have a delay between the two signals, I have a system that is out of phase, or there is a variation made by this phase angle. Okay, so the formula that we have for impedance is the impedance in function of the frequency is a delta potential in function of frequency divide delta current in function of frequency, where the impedance is a complex impedance. Why is a complex impedance? Because we have a positive and negative value. We have an real impedance and an imaginary impedance. So this is the main concept that we have from impedance. My last slide for theory, then I finish, is about the sinusoidal system that we have in between. So keep in mind this sinusoidal information. How we present the impedance. I finished the torture with the theory. Don't worry, it's done. How I represent my impedance. My impedance will be represented in different plot. One of the most important is the Nyquist, where I have the real component on the abscissa. The imaginary component are the ordinate, and this plot is minus, normally is minus imaginary versus real impedance with isometric axis. The Nyquist is very well recognized, so everyone is using impedance is normally use the Nyquist. It's very well recognized, but you have no frequency information. There is no frequency information. And sometimes at very low value of frequency, I don't know what's happened. For example, here, I see this data, I said, oh, this is a very nice data, but I don't know what's happening in this small corner. And when I zoom in there, I found a nice semicircle. So the important is always, I always say it when I go to any conference, any meeting, to see also another plot that is less popular, but is also very interesting, and is called Bode. The Bode plot is interesting because in this plot I have the phase angle information and I have the frequency. So I can see what's going on my system for all the frequencies. So the Bode plot is made like this. I have to one side impedance, the total impedance versus frequency, and the other I have the phase versus frequency. So with the combination of the two plots, I have a complete overview of my impedance data. So my suggestion, personal suggestion, is whenever you present the data to other people, you want to explain what's going on your measurements, use both plots. I'm always joking with the students when I'm going to a meeting and say, where is your Bode plot? How is the Bode plot? Because it's very interesting to see and give you more information. Why give you more information? Because at the end of the day, your impedance data is a three-dimensional data. Where, if you watch on these sides, you see the Nyquist. If you watch on these sides, you see the Bode. And if you watch from the top, you see the other Bode. So this is your impedance data. The floor is your real data. The upper part is your imaginary data. If you watch with a three-dimensional plot of impedance, you open your mind about how is the structure of the impedance data. The impedance is a three-dimensional plot where your ground is your reality, the above is your imagining, and the underground is your inductance. Question? Nice. Have you seen before like this? Okay, I open a new door for you. Okay, now the interesting part is, yes.
Because people going to the other section, someone in the audience asked what is the best DC voltage and AC current that we can set for different indexes?
Je ne sais pas. I don't know. It depends a lot of the system you analyze. There are cases where I'm working with a corrosion, where I'm using to apply even not a potential, but apply current zero, because I'm sure that with a current zero, I'm in full equilibrium. There are cases where I want to see my measurements, my reaction, so I apply a potential to destroy my sample and see how it's changing my impedance. So it depends a lot of what is your cell. So which is your system can change the value. For example, if I'm working with a battery, I want to see the impedance as a full battery charge, so I apply the potential of my battery to charging my batteries full, or I use a discharge potential to analyze what's happened when my battery is empty, and for be very sure about my battery is empty. So there is never a correct value or an exact value. I can say that the majority of the people are using what is called the open circuit potential. So that is the natural potential of your cell. But now we will see some cell setup, and you can decide how much can be the value from your cell. I hope that I replied the question. So the cell setup, how I can do the cell setup? Like we mentioned, the potentiostat normally provide for connection. So I am the working electrodes, I am the counter electrodes, I have the reference electrodes, and I have the sense. So in my system, normally, let's say the majority of the time, the sense and the working are connected together. So, but again, there are some cases where you use a for connection and the things can change. So this is the normal electrochemical interface. So what we are seeing what's happened between our working electrodes and our reference electrodes. So here, what's happened in this small portion of my cell. So in this situation, I have my working electrodes and my reference electrodes, and the nice flowers that I see there that looks very pretty and yellow are not flowers, but are ions that are going out from my working electrodes to the solution, or depending to the equilibrium, are going from the solution to the working electrodes. Depends to how is the diffusion in my setup. So this is the normal situation that I'm seeing in the system. Okay, this is a less romantic view, is the electrochemical view of the setup. So we have a resistance of the solution. We have a resistance or charge transfer resistance of my material. I have the diffusion of the setup, and I have the double layer capacitance. You manage? Yes. I need your battery. No, no need. No, I can see. No?
Yes, that's the problem.
I'm not on the proper angle. or I'm too far from the angle. Maybe I'm. Yes, here it is. Okay. Sorry, sorry. Okay. Let's see the elements that we have in our cell. So we have the first elements that I want to talk is called the charge transfer resistance, and is the resistance of our material. So our material has a resistance that depends to a lot of information. The first resistance is called charge transfer resistance. If you are a corrosionist, you call polarization resistance, is exactly the same. Is based on electron transfer kinetics, temperature of your electrodes, composition, morphology. Which value? The value is everything. Can be from milliohm, when you have very fast kinetics of the electrons passing through your material, to the gigaohm, when the electrons are very slow, if your material is not conductive. The fastest elements we have is the silver. It's not the copper, it's silver. Silver is the most conductive material we have. Then we have the more or less or semiconductor, like a silicon, not conductive, like a Teflon or glass. So depending to which materials, the reaction, the kinetics of your electrons can be very fast or not. Then going from the internal to external, we have the double layer capacitance. Double layer capacitance is difficult to understand for the normal electronic people, but it's something that is very chemical. So are the distribution of the charge in front of our working electrodes. Somebody call also diffusion interfacial capacitance. You can call as you want. And the most important is these elements depend to the concentration of our ions, depend to the type of ions we have, depend to the surface of our surface, depend if you have some absorbed spaces or not on the surface. So depending to the value. I found this table pretty interesting to see. For example, in bare metal, we are about from 10 to 50 microfarad. An oxide layer, we are around 2 microfarad. Aluminum oxide at 0.5 microfarad. But then you see very strong coatings, we are at level of picofarad. So depending to how is the situation is changing step by step. The next element that we see is what we call the solution resistance. The solution resistance is also called uncompensated resistance and is, at the end, the resistance between the reference electrodes and our working electrodes. Depends to the concentration, depends to the cell setup. If they are very far or very close, this resistance can change. Depends to the temperature, the conductivity, the type of ions I have, the mass transport, depend to many factors. The value. Normally, if we are in aqueous solution, we are talking about around 100 ohms. I give you the comparison is KCl at 0.1 molar at 20 degrees, 85.69 ohm. So this is, they use as a standard to check the conductivity. Above 10 kilo ohm, we have organic solvent. Below 1 milliohm, we have the battery that is very concentrated salt and is very conductive. The last elements that I want to analyze is the diffusion elements. That these diffusion elements is called also Warburg or constant phase element 0.5. So is an element that is called also semi-infinitive diffusion, depends to the temperature, the concentration, the diffusion coefficient, viscosity, electrode area, and really there is not a typical value, it's depending really from the system. And normally is show as this line is 45-degree line, and this is typical diffusion element. Now, I want to go, let's go a little bit faster about the circuits element. And this is a typical impedance diagram. So this is how the diagram of impedance, how to analyze the data. And the most important is, what is the difference between resistance and impedance? So we are talking about the resistor when we have a DC system. And we are talking about impedance when we have an AC system. But again, when we are talking about AC, we have not only the resistors, but we have a capacitor and we have the inductance. So it's a complete setup of the three elements. So resistance, capacitor, inductance, and then we have some other mixing of the setup together. Again, definition, impedance has the same measurements units of resistance, is ohm. The reciprocal of impedance is called admittance. The frequency is normally in hertz. It is the same of S minus 1. And the impedance can also be normalized by the surface. There are some cases that you see impedance per centimeter square or permittivity. So there are also other definitions. Let's starting from the beginning, the resistance. So the resistance is normally always the same of the impedance. So impedance and resistance are always the same. Whenever I analyze a resistance, the phase is zero. What it means, the phase is zero. When I measure or send a signal of potential, the measure signal in current are exactly in phase. So they start from the same points, they finish at the same points, phase. Now, if I see the Nyquist of my resistance, I will see something like this. This is a point, this is a point, this is a point. They are all on the same place. Why? Because I have no imaginary points and I have only real. So the value that I see are always around. Probably there is small variation, but they are all around. Phase, it's easy, zero. And the value that I can see on the module is the value of my resistance itself for all the frequencies. So no change, is a strict line. Now, when we're talking about capacitor, it's a little bit more complex. Why? Because when we are talking about capacitor, capacitor is frequency dependent. So there is an frequency variation inside the formula. My phase is pi greco half, so it's 90-degree variation. So what it means that if with resistance or impedance we were in phase, with the capacitor we are out of phase. There is a small modification. The Nyquist, we have no real part, only imaginary. And again, you see the bode, there is no information about the modulus, so it's starting from where and finish somewhere, and the phase value you see there is minus 90 degrees. When I take the inductance also is frequency related. The phase is plus 90 degrees. So if the resistance, you see here, the resistance in phase, the capacitor is out of phase from these sides, the inductance is out of phase to the other sides. Okay? So the points are all in imaginary sides, but is reverse imaginary. And I have no information about my module. Now, let's see if I put I'm very bad. I put together a resistance and a capacitor in series, one after the other. What's going on in this case? At the beginning, I will measure my resistance. So I have a shift on the value depending to the resistance I have in the front. And then I have all my imaginary parts following. When I see these sides, you see here is 0, phase at 0, it means that I'm doing the resistance, and then it's going up to 90 degrees, where I have my capacitor, one after the other. If I put the two elements in parallel, first points and the sequence points are imaginary, and at the end, I will see my real parts. So again, in these sides, the first part is imaginary, and then I have real. So first, I will do, in this case, double layer capacitance, and then the resistance. The simple electrochemical cell model is called Randle cell. So the cell that we have seen before is resistance of a solution, double layer capacitance, and charge transfer resistance. When I put these three elements together, I have first resistance. So you can see from here the resistance first, then it's going up to do the double layer capacitance, then it's going down to do the second resistance. Here is the same. At the beginning, I have one resistance, then I have points where my modulus is very uncertain because I have the presence of my double layer capacitance, and here at the end, I can see the second resistance plus the first resistance. Here is the same. At these points, I have my first resistance, then double layer capacitance, and then the second resistance plus the first resistance. And then I have what is called the RC or RQ semicircle. So the Nyquist plot, at the beginning, at the end, where I almost touch my base, so the real part are in phase. Then here are outside of phase. Here is totally out of phase. And again, now you can see this three-dimensional plot. So again, here you have your Nyquist, your Bode, and your real part, your imaginary part, and on the underground, you have your inductance. It's a little bit more clear now. After 100 times, it's becoming clear, then you get it. But it's just to figure out that whenever is above is imaginary, whenever is ground is real. So when you see the Bode ZR, so this typical S, this is only on the floor because you have only resistance there. You have no data about impedance. Whenever you see the Nyquist, all this very nice semicircle, you have always only imaginary part. So it's whatever is above is on this semicircle is imaginary. And it belongs to a capacitor and not about resistance. Still with me? Yes? Good. No question from outside? No, they are all. How many instruments you buy? Yes, of course. Okay, this is very true whenever you follow some specific rules or condition. So whenever you do these measurements, you need to be sure about what's going on your experiment, because of course it's very nice semicircle, wonderful impedance, works. No, you need really to follow some rules if you want to analyze your data. And I write this: keep calm and follow the rules. So the three rules or fundamental conditions for impedance are linearity, stability, and causality. I will try to be a little bit more stronger on this. So linearity condition: whenever you apply an AC amplitude, must be small enough to get a linear response. So the first rules say to you, be careful about the applied amplitude of your frequency. Because we are here. You see, the signal is not regular. Is on this tendency. It's not a very nice line like this, but there is a tendency. So, and whenever I reply on this amplitude, my response has this amplitude. So I must be very sure about the amplitude I have. So remember about the signal I have. Now, many, many years ago, when I was young, full of hope and full of air, people are using to read impedance by a Lissajous. A Lissajous plot is nothing else but a plot where I have current and potential in one single plot, and this semicircle is changing every time I'm changing the value that I'm analyzing. So if I have a pure resistance, it's a line like we have seen before. If I have a pure capacitor, is a semicircle. If I have a combination of capacitor and resistance, is an ellipse. So at the time of dinosaurs, we use the oscilloscope to analyze the data, and the people were there with measurements with a pen and rules and see the system, and the impedance were calculated in this way. So you are lucky to have a system that analyze and give you the response immediately. You remember?
I remember very well.
So you see, the white hair is, that's why I'm not having white hair anymore. So it's, he remembers. So we are from almost the same age. So we remember when we analyze. We were around the time of dinosaurs, so we know about these kind of things. So today you don't have to fight with these kind of things, but it's important to understand one single process that is behind the impedance. Keep in mind that the impedance that you read in the Nyquist plot and in the Bode plot is calculated. The raw data is this. This is what the equipment made. Then they calculate for you and say 42. So is difference from the value that you read in the instruments and what is made by the system. This is what there is behind. So it's always an frequency amplitude, and it's always potential current. But then, of course, we are not so bad, and we give you directly the real imaginary value and so on. So, coming back to our system, keep in mind that we are always in non-linear condition. Keep in mind that whenever you apply a signal, depending to where you are, the response is also not linear. So you can have something like this, you can have something, you see, depending to how is the variation, the response can be different. Keep in mind that like we mentioned a few seconds ago when the person made a question. I work on apply potential or I work apply current. The impedance is independent if you're using the potential or current. Which potential or current I apply depends to the system. I can apply open circuit potential, I can apply different potential. And what should be the AC amplitude then? So how I can choose the amplitude? Small enough to be in a linear part, but big enough to get a response. After I will show you some case where it's important to have this. So it depends to the signal to noise ratio, because I have noise everywhere, so I want to be sure that my signal is independent. So the impedance is independent from your amplitude system. The second rule is what we call stability rules. So the state of the system don't have to change from the beginning of your measurements to the end of the measurements. Need to be the same. So it's very important, the frequency range and the measurements that I'm using. For example, if you have a corrosion, your experiment at the time zero, your experiment at the end of the measurements should be the same. Otherwise, everything is changed. So I needed to be fast to get the majority of the information in a stable system. The discharge of the device, I'm doing a battery. I need to be sure that at the time that I made the measurements, the battery has the same value for all my measurements. Remember, normally the electrochemical systems are unstable. So the first information that I can use for be faster and get my measurements normally for a few range of frequency easy, it's do a frequency scan from high frequency to low frequency. Why? Because the high frequencies are faster. So I can get more points at the beginning and less points later. The experiment duration depends to the low frequency limits. Lower is my frequency, longer is my experiments. How long can be? These are some experiments. So keep in mind for do one single frequency at 10 microhertz will take 10,000 seconds. So more than 3 hours. And it's one. Sometimes the instruments want to do, one is not very good, let's do it another one. It's another 10,000 seconds. And scan from 10 kilohertz to 1 millihertz 71 frequency with logarithmic distribution will take 4 hours and 45 minutes estimation. With the 24 bits resolution, that is new techniques that the people are using for some instruments, will take 1 hour and 30 minutes. It's faster. If you do the same, more or less the same number of frequencies from 10 kilohertz to 0.1 hertz, it will take 3 minutes. Why? Because the higher frequencies are faster. There are some alternatives, yes. One of these alternatives is called multi-sign. Multi-sign is a technique that some equipment has inside and allow you to do more frequency in the same time. So it's doing a kind of calculation, superimposes different wave, normally are 5 or 15, or there is also some even more, when they superimpose all the frequency in one shot and send it to the data. So this is a multi-sign, for example, 31 sign in one shot. Looks like a very confused system, but at the end, you have 31 points in one shot. It's noisy, yes, but at least I can be faster for my measurements and reduce the time of measurements. The other alternative is moving the frequency range or be sure that your system is as much stable as possible. The last condition is what I call causality condition. This depends 100% on you. And the measure of my response is correlated by the AC stimulus. So it's very important, shield the cell using a Faraday cage. So use a way that you keep outside the perturbation of your cell. So don't go in front of your cell with a mobile phone, because you believe or not, you give some influence. Remove all the extra cable. Between the reference electrodes and the instruments should not be any cable extra. Sometimes I'm going, I have one cable, a crocodile, another cable, a crocodile, another cable, a crocodile. Every cable you're using, you have an antenna there. You catch all the television and radio on the neighbors. Crocodiles are very dangerous. More crocodiles you have, more oxidation you introduce, more noise you have in the system. So keep in mind all these kind of tricks when you do your measurements, because this is the problem. You catch noise. And if you are measuring a very, very small signal, can be that the noise is higher than your signal. And then you don't catch any information. And there is another problem that you have behind. One of the problems is the 50 hertz. I don't know, you have a 50 or 60 hertz here in Canada? 50. So this is a typical 50 hertz presence. So sometimes you plug the cable and you have no ground connected, and then you have this problem in your measurements. Question? Question from abroad? No. Okay, they are totally suicide. Okay, let's do some case study for opening your mind, our mind, about some different elements or different way to see the electrochemical noise. I put some specific case from corrosion studies from battery, fuel cell, solar cell, and catalysis to open our mind that the impedance is not only capacitance and resistance and inductance, but there are also other elements around. The first one belongs to the corrosion, and the goal of electrochemical corrosion is to determine the corrosion rate, and normally the corrosion rate is in millimeter per year in a fast and sensitive way. The determination of corrosion can be made quantitative or qualitative, and normally you're using a very nice corrosion cell to do this experiment. Now, where the AC techniques is entered. Why? Because the AC can distinguish very well if you have a reaction in the cell, if you have coatings. And corrosion with impedance is very important to analyze if I can identify some diffusion problem. Remember, very interesting in corrosion, the techniques can be very sensitive. Okay, let's have a look in reality what's happened. We have normally something like this. This is our material. We have, again, our cell. We have our working electrodes. The blue there is the reference electrode. I'm zooming in between. We have the resistance of the solution. We have the double layer capacitor where the charge are located, and we have the resistance of our material. So at the end, we have a very nice random cell of our system. Now, with impedance, we have a lot of information. We can use software to analyze the data, but normally when we are talking about corrosion, we have 4 kind of circuits in front of our eyes. The first is where I have a very high resistance coatings, where I have a conductive coatings on steel, where I have just steel and bare metal in a system, or when I have corrosion in my material. So these are the 4 situations where I can see my setup. The first elements that I'm working when I see corrosion is what is called Warburg impedance. And the second elements that we see a lot in corrosion is what is called constant phase element. These are the two elements coming from corrosion, difference from whatever we can see around. Okay, let's walk in about a very high full intact coatings. We have a very nice Teflon or a very nice film deposit on our steel. You have a very nice car with your very nice paint on the surface, very cover, very nice. So this is a very ideal situation. So this ideal situation, we have normally a resistance and double layer capacitance. Why? Where disappear my resistance of a material? Is behind the coatings. And due to the fact that the resistance is very high, we can also mention that for our setup, our measurements way, the resistance is infinitive and is above the connection or the capacity of the instruments to measure. So if we do this setup, we have something like this. So the resistance here is the resistance of a solution, and then we have the double layer capacitance that in theory, if the double layer capacitance is perfect, is 90-degree line. But it's not 90-degree, there is a difference. Why? Why there is this difference? Because it's not a pure capacitor, it's a paint, it's a membrane that we place on our sample, is something that we deposit above our sample. So the electrochemical people, what they said, it's not a capacitance, it's not exactly the same. So we call these elements Q, or constant phase element, and they describe as an imperfect behaviors of the reactants. So they call Q, and you see the Q inside the formula as this small n. And they say when n is equal 1, so all these kind of things is becoming equal a capacitor. When n is equal 0, of course, this one is becoming a resistance. n at 0.5, we have a uniform diffusion. Between 0.5 and 1, we have a rough electrodes. Between 0 and 0.5, we have a porous electrodes. These are definition. Then you can have a porous electrodes with higher, you can have rough electrodes with lower. So it's more or less a definition. On one side, you have smooth electrodes, very nice electrodes, perfect. So in the front of these electrodes, you will have a pure capacitance. On the other side, you have a rough electrodes. On that side, you have a rough electrodes, so a constant phase element. To give you an idea, where is the situation? This is constant phase element 1. I have a perfect semicircle, but if it's 0.9 is get a little bit flat. 0.8 is even more flat, and you can imagine 0.3 is almost very, very flatty things. So lower is the n, flat is my semicircle. Now, if I'm doing the fit and simulation and check this situation, I will be something like 0.94, something like this, and I'm fitting perfectly my data. So when you see something that is not a perfect semicircle, you have to think about, hey, that one is a constant phase element. That one is not a pure semicircle. I'm sorry to tell you, but 99% of the time, you have a constant phase element. Until you're not watching a pure capacitor, but forget about a pure capacitor. Leave to the theory, leave to electronics people, you have a constant phase element. I'm sorry to give you these reality things. So you see, you can go a very, very high impedance. This one is 1 gigaohm. So sometimes I see we had also specific instruments that go at 100 gigaohm. So you can do very high impedance if you like, but keep in mind this situation. Then the second part is when I have some corrosion. Can happen. We are working in this world where we are in imperfection situation. So you have small parts of your working electrodes that is corroded, you have the rust, you have this situation. So what's happened? In this case, you don't worry, you don't need to commit suicide, but you can think about that your corrosion is nothing else but a mass transfer. Your working electrodes is becoming part of your solution. Of course, there is also some rust in below, but it's becoming part of your solution. So you have a transfer mass from your working electrodes to the solution. And this transfer mass, you can see as this line that is called semi-infinitive diffusion. So your setup now has a 45-degree angle and is becoming, Warburg made this study many, many years ago. It's even older than the Ladles and the Tafel plot. And in high frequency, you have a kinetic control. In low frequency, you have a diffusion control. And in between, you have a mixing control. So don't get worried. You have this Warburg. This is the formula about the Warburg, and it belongs to the coefficient diffusion, the temperature, the viscosity, and this is the mixing part in between. So the Warburg, it's easy. It's depending to the diffusion, your semicircle can change, it can explain, and you can have this. The last elements that I want to show you is when I have some metal coatings or some conductive coatings. So in this case, this is my setup, but then I have my metal, I have my electrolyte, and in between, I have the coatings. And the coatings I analyze as another resistance and double layer capacitor. So if I'm lucky, my coatings is enough valuable to read, I can see, in this case, two semicircles, one for the coatings and one for the metal. Now, the coatings can change depending to the thickness. My resistance can change and can expand the semicircle like this. Very important. I can write my system in all this way is exactly always the same. The software doesn't know if the two RQ are separate, are connected. Few years back, I remember around 20 years ago, they said that when they are together is because there is no variation or no modification between the two are separate. It's like the software doesn't care. So can be one, can be the other. And if you're going in a Congress and you met some Russian that ask you why it's like this, you say this like this because it's like this, point. Don't go into the discussion with the Russian on this. So the software is analyzed in this way: resistance, double layer capacitance, resistance, resistance, double layer capacitance, and sometimes you have a diffusion at the end, or in this case, not. So this is the circuits that I show you at beginning. And now you know why I show you these circuits at beginning and why impedance is very important, because I'm able to analyze the complete overview of your system. Now, this is for corrosion. Battery can teach us other elements, very interesting. Why battery is interesting? Because battery has DC voltage offset. I can apply different information. The techniques are interesting for impedance. And I have some specific influence about the measure of equivalent series resistance and some mechanism failure on my system. So normally with battery, I work in a galvanostatic way. So I apply a current and measure a potential. This is a typical battery system. So what I have here is the beginning of my measurements. You see, I have this negative part that we already know that whenever I see a negative part is an inductance. You remember it's below the floor, so the ground zero. And this is a typical impedance with a battery changing the state of the charge. State of the charge is how much charge I can have on the battery, and this setup is changing. So the circuit is an inductance, resistance, double layer capacitor, the resistance, double layer capacitor resistance, and diffusion at the end. Nothing else. But there is some elements different, and one of these is called tangent hyperbolic diffusion. What is a tangent hyperbolic diffusion, and why we have these elements? These elements because we have a thickness of film in my system, and the impedance is not exactly the same as my Warburg. There are some difference because my film is conductive. I have some porous electrodes. I have some difference. And where I can see this difference? Because my line is not anymore 45 degrees, like I've seen before in my corrosion, but is more than 45 degrees. And here I don't have a corrosion, it's a battery. So why I have a diffusion? It's a diffusion, but is an electrodiffusion in and conductive surface. So if I want to see these elements, this is the equivalent circuits, and I don't have a Warburg, but I have these elements called T. T is called tangent hyperbolic diffusion. On some software you call finite length Warburg open, so you can use a different name. But at the end, what is important is a conductive surface is still an mass transfer, but in another way. So there is another element that this one, just for you in a few words, is called Gerichter impedance. This one was at the beginning of the history of the first lithium-ion batteries, more than 25 years ago. And this is some porous electrodes elements, and just to know that there is this also these elements, Gerichter impedance. It's not used anymore, it's not popular anymore, and was for the first lithium-ion batteries, and this is the impedance data of this. And the element is called G, or Gerichter impedance. You can have also some mixed diffusion. This is a beginning of Warburg, and then it's going up at more than 45 degrees as a T. Now, the fuel cell is also give us to explain two new elements. Fuel cell, in this case, we have what we call a solid oxide fuel cell that they are working at very high temperature, between 600 and 1000 degrees. And in this case, we have some elements that we can see here. We have an first part that is our inductance. We have high frequency charge transfer, anode gas diffusion, and cathodic surface process at the end. But this is not an RQ, but is another kind of diffusion. This diffusion you can see is this semicircle that you can see at the end is called finite diffusion, or O, or cotangent hyperbolic diffusion. It's again a mass transfer to a thin layer or a coatings. Sometimes the people call Nernst elements to adjust the model of the system, and the symbol is an O. And how is working? I have a very nice show. Let's see if it's working like this. So this is the diffusion layer, and this is the elements about this diffusion. So it's a semicircle at the end of your measurement. It's not an RQ like you expected, but is a diffusion itself. I have this one that is an inductance. We have already seen that the inductance is everything that is negative in our measurements. We have two kinds of inductance. One is high frequency inductance, and one is low frequency inductance. The high frequency inductance, it means that you, or the experiment, start at the wrong frequency range. So you are asking the system to analyze something that is not belongs to the cell. Because in theory, at the beginning of your cell, you should see the resistance of a solution, these points. These points that are made before is because you are using a higher or larger frequency range. So you made these problematic measurements. So this is not belongs to your measurements. You can remove easily. There are some special connections you need if you want to use high frequency. But sometimes you have an inductance at the end of the measurements. So you see the inductance is here. And this one is not a problem of wrong frequency range. This is part of your measurement. So what's happened? You have an absorption process at the electrode surface, and you have a surface reaction or a chemical modification of a reaction. So the system, you start with something, and after the measurements, this something change. The resistance of this something in your cell change. So in this case, I have this modification, or I have that very nice circle on the system. So in this case, I have an inductance in the middle or at the end of my experiment. This is typical on fuel cell, but sometimes you can see also on corrosion, you can see in other experiments. That, for example, if you made analysis of nickel, in the nickel, in corrosion, you will see a huge amount of these variation. Because nickel is passing the measurements. So, for example, these are some article about, and the nickel is passing, for example, from nickel 2 to nickel 4, and this modification give this variation on the resistance. Okay, the last points, I'm going very fast, is on solar cell. So on solar cell, you have an instruments and elements that is called transmission line. Transmission line is these complex measurements typical from the solar cell, and is named by the discoverer or their main person that apply, called Bisquert, and it's called Bisquert2, these elements, and this is the complex of transmission line. But it's problem for the people that are doing dye sensitized solar cells, so this is more for their life. Then on catalysis, the last elements is on catalysis. I will be really fast, is an oxygen reduction. Sometimes you are using an hydrodynamic system or an rotating disc electrodes, and in this case, the variation of your elements due to the variation of rotation, you have this modification. You have not anymore a linear diffusion like you expected, but you have an closed diffusion. So instead of being an 45 degree, your diffusion is closing due to this hydrodynamic setup. So faster you're going, closer is your circle. Okay, 2 words about the experiment design. Are you still with me? Alive? Okay? Believe me, I am almost finished. My watch didn't work, so it's perfectly. I have always time for you. Okay, experimental design, the setup, the sample, the cell, time domain, frequency domain, potential static galvanostat, setting of the impedance, analysis of the data. One day if you want, but I will do it in 20 minutes, less. Sample can be liquid, can be solid, can be gas, can be colloid, can be electroactive or not, room temperature, high temperature, low temperature, doesn't matter. All this case, I can do my impedance data. I did also impedance in gas, is a mess, but you can do it. Very important, Faraday cage. Remember, Faraday cage is fundamental. I needed to keep outside my mobile phone from the experiment. Shorter cable, proper reference electrode. What it means, proper reference electrode? If I want to use the reference electrodes, I need to be sure that my reference electrode has a good exchange from the inside to outside of the solution. If I don't have this knowledge, I will use what is called a pseudo reference electrode, or I threw it away, the reference electrodes. Doesn't matter. Battery holder, it means the battery needs to be very placed in a proper way whenever I do the experiment. Remember, causality condition. Experimental design. Our potentiostat has 4 connectors. Can work in 2-terminal, 3-terminal, or 4-terminal. It's up to you which condition you want to use. Keep in mind that the current are going from working and counter. The potential is measured by the reference and sense. There are 2 ways to analyze the data on impedance. One is called time domain and one is called frequency domain. The majority of the experiments are always in one setup, always. So these are the time domain is a sine wave in a modification, and the frequency domain is by amplitude. When I use one and when I use the other one, depends to equipment that I am analyzing. Our system normally is always the same, is an time domain, and we are using always this system. But to give you an idea, time domain is whenever the DC potential is applied, and frequency domain is where I don't apply any DC. So the old-fashioned equipment where I have only the impedance, they not apply any potential, they not apply any current, they just measure the impedance. In that case, I have what is called the frequency domain. These equipment were used due to the fact that I don't have a potentiostat galvanostat, are using when I need to have very precise measurements. In some specific case, I will use the typical instruments without a potentiostat. I will show you which one and which are the problem. Whenever I want to go at very high frequency, then I can use these time domain. There is also the discussion, they always say it in electrochemistry against material test, because time domain is typical from electrochemical people, where I have liquids, where I have an open circuit potential, where I have 2, 3, 4 electrodes. And frequency domain is when I don't have, normally I have a solid sample, I have a material measurements, I have a 2 or 4 sample, and this is the experiment. So from this side we have the chemistry people, to the other side we have the material people. So which one you prefer, you are belongs to the other. Now let's talking about the experimental very fast. Which potentiostat or galvanostat? Which potential, which current? As I said at the beginning, the majority of my experiments are at open circuit potential. So normally I read the potential for the cell and I apply that potential. But I can also apply a fixed potential or a fixed current or a potential scan. So a few years back, there were a lot of people using potential scan to analyze some semiconductor. There was a technique that I will explain in a few seconds that is called Mott-Chomsky plot. And in this case, you have a potential scan. There is also time scan. If I want to use the same frequency during the time, I can do a time scan. So this one was a Mott-Chomsky, but the flat band potential was the intercept. The slope gave the number of dopants. And this one was a plot for semiconductors. When I want to do a setup for impedance, I have 3 information to keep in mind. One is the frequency range, one is the amplitude, and then if I want to work with a single sign or multi-sign. Remember, multi-sign is when I want to work at very, very low frequency and I want to analyze what's going on at the low frequency. Why the frequency range is important? I show you one data. This one was many, many years ago made in Japan from my friend Suzuki-sama, but it's very important to understand why the frequency range is important. Here we have an experiment from 1 megahertz to 100 millihertz. Now, here we have 2 mistakes. two error. Two error. Somebody knows the error? Okay, the first error is this part. We start at very high frequency. We have this inductance that is not belongs to our system, correct? Okay, so if we analyze now, we have the second error. And the second error is that we finish at that point. Finish at this point, what means? It means that my measurements is not end. My measurements can continue in two different ways. No? Okay, this is the first problem, and can finish in this way, or can finish in this way. Many, many years ago, I was in Malaysia, and I went in the laboratory, and the students showed me, I have this data, and I said, okay, wonderful, how long do you work on these data? 6 months, okay, you threw it away, your 6 months of work. They want to kill me, but it was not my fault, it was their fault, because the problem is the data is incomplete. You don't know if you have a diffusion like this, or you have a very nice semicircle like the other one, correct? Are you with me? So it's important, the frequency range. Whenever I arrive in points like this in the middle of nowhere, I said I needed to go at 10 frequency more or 20 frequency more to understand what's going on. And actually what's happened, instead of using 1 megahertz, 100 millihertz, we changed the frequency from 100 kilo and 1 milli, takes longer measurements, but you see I have a very nice and wonderful diffusion. So it's important the frequency range. When I do the measurements, if I see something that is finishing 1 point, I say, Luca told me that to go a little bit further. Let's go taking a night to do the measurements, but let's finish the measurements and see what's going on. There are some hits that you need to keep in mind when you do the measurements. With reference electrodes, your higher frequency will be around 50 kilohertz, 100 kilohertz. This is a big limitation of your reference traditional electrodes. Whenever I use the booster, my maximum frequency is 20 kilohertz. Don't think to go at higher frequency. When you go to high frequency, remember the inductance. When I go at too low frequency, remember the stability. My measurements can take a long time, and then my solution can evaporate, I can have a corrosion, and all these kind of things. Anyway, remember also the contour plot, how is the limits of my measurements itself. Okay, the last point is about the frequency amplitude. I have a very fast system to explain, and is this. The frequency amplitude is like this. Okay, let's think about these measurements. This is a non-conductive system. So you see the central part from all this potential, let's say from minus 150 to plus 150 is very stable, is 0. So I have no current. So what it means, I have no current variation. That if I analyze the 2 points, here, I can apply an amplitude of frequency of 100 millivolt, and I have a variation on current of 0.18 microampere. 200 millivolts, it's very linear. So no variation at all. So it's following perfectly the Ohm law. So what it means that the system is very stable. I use 1 millivolts, 10 millivolts, 100 millivolts, nothing changed. Okay, what's happened if I analyze the second part? 10 millivolts give me a current of 20 microampere. 50 millivolts, 160 microampere. I'm in not linear condition. So what it means that I needed to be careful, and maybe instead of use 10 millivolts, probably it's better to use 5 millivolts or 2 millivolts. So not using a big amplitude, because I will generate a lot of current. Okay, so remember, the amplitude belongs to this fact. I needed to be sure what is my amplitude that I use. The standard on the equipment is 10 millivolts, but is not covered on the marble. You can change depending to your system. If I'm using a not changing material, like a very stable or a very non-conductive or a membrane or plastic, then I can use 20, 50. So thinking always, this is very non-conductive material. If I have, my material is some gigaohm, okay, at 20 millivolts, 6.151 gigaohm generate a current from the instruments of 3.2 picoampere. Picoampere. Okay? Picoampere is very small. It's 10 a la minus a lot. So remember, gigaohm generate picoampere. What it means that if I have a gigaohm, maybe I can use, instead of 20 millivolts, I can use 100 millivolts. But then my error can be less. Now, we finish our measurements and we can analyze the data. To analyze the data, there are some software. The most common is the ZView. There is another software that is called ZSimWin that is more simple. And always remember the elements. These are the standard elements that we see everywhere, is resistance, capacitance, constant phase element. Then we say that we have a Warburg, the finite diffusion, the bound diffusion, the Curie impedance. But there are hundreds of elements. This one, only when I opened the ZView software, I found that there is this, the V por finite length. So there are a huge amount of elements, and even the elements that you write what you want. You write the equation and you have a fun with the equation that you like. So if you want really to have your elements, you can have your elements. So you can write and prepare your elements. But the most important things that I always say is you must know what you are doing. So you needed to know which system, which is your setup, if you have a conductive layer or not, if you have an insulation layer or not. Because if I show you some data like this, and I don't say it with this, in the past it's happened to me that the people send me the data and say that I made my measurements and this is my measurements. I say, wonderful. I send back and say, what is your measurements? Because that one can be everything. We have seen that this one can be, thinking about this one that we see there. The process can be this, can be this, can be this. 3 equivalent circuits, in this case, probably even more, and can be everything. Depends, are you in a solar cell? Are you in battery, corrosion? Which is your system? So depending to your system, this analysis can be everything. Can be here, this semicircle can be a G, can be an O, can be another RQ. So can be, sorry, this one is like this. Can be everything. So you need to know which is the correct elements I have here. Because you know if your elements is conductive, maybe is this, is an G, or maybe is not conductive, then is normal RQ. So you know which is your elements that we analyze. So in this case, this is the process. And I show you we have 3 circuits, and all can be the correct one. So it's important to know which is the system. Now, very fast on the instrumentation. We have still 2 minutes, Dario? Yes? Thank you. Okay, this is the instrumentation. These are the instruments many years ago, but still alive. So the important to understand, I can have a potentiostat with impedance. I can have the impedance standalone. So in all cases, I can have everything that is coming with impedance. Whenever I have a DC potential applied or DC current together, I can have this kind of equipments. Whenever I have only impedance, I have these Solartron instruments. These are the software. You can have all the software you want. A lot of people are using our software in another equipment, doing measurements from one equipment to the other. The important is keep in mind the circuits you have behind. Another important feature that you have to keep in mind is that plot that is called contour plot. In this contour plot, you have the impedance of your system and the frequency. So why is important? Because if you want to do a measurement at higher frequency, higher impedance or lower impedance, and it is outside of this contour plot, you are going outside of the scope of the instruments. So the instruments is not capable to do these measurements. So it's very important to keep in mind this contour plot, and it's very important to understand the error that you can have behind, because the blue part, the dark blue, is where the instruments is working well. The other one, you can have 10% of the error. So 0.3, 5, it depends to how far you're going from the measurements. So for example, this is the top of the Solartron, and you see the central part is 0.2% of the error and 0.2% of the degree of error. But if I'm going on this part, I'm already very high error. So what I measure can be correct or not. Then there are some part of the measurements that I can use to increase the capacity and going more at higher or lower part. So sometimes people come in with very nice batteries and say, oh, I have a battery and I'm doing some micro-ohm. Micro-ohm, you are here. So whatever you measure, it's outside of this contour plot, and it's very difficult for the equipment give you exactly the error. So your measurements can be, let's say, plus minus 100% of error. So it's important that you keep in mind this contour plot of the equipments we are using, the response of the measurements, whenever you do the setup. So the blue area is the comfort zone, and then you can go sometimes higher and lower depending on the measurement, but to be sure about your measurements itself. So this one, for example, is the material stuff. So you see the error is very low, and the range is going to beta ohm that I even don't know that exists before watching this plot. So the beta ohm is even higher, but again, is something at level of the system, and you see the error are even lower. Okay, some other points very fast. This one is what we mentioned, is localized impedance. So give you the idea to do the measurements in localized points. So I do the impedance points per points at the level of micron. I can do a frequency range for each point or apply one frequency for all the measurements of the surface. And I can do localized impedance on specific sample. It's really interesting for some micro range, and you see the plot, you see the value directly in impedance. So you can analyze the impedance on your surface and mapping on surface. So these are other potentials. So keep in mind the contour plot when you do the measurements. Okay, so accessories, Faraday cage. Again, I insist, Faraday cage doesn't matter that you buy an expensive Faraday cage from us. You can use a metal box. In some place, I use a biscuits can. In other place, a garbage bin in the top of the cell. Insulate and connect the Faraday cage to the ground cable. The ground cable is not there for waving, and so but is to connect on the Faraday cage. So doesn't matter, using aluminum foil, whatever you like, even a plastic box with aluminum foil, external and internal. It's fundamental for your experiment. High temperature, low temperature, doesn't matter. So the fundamental, I said already, but I will say it again, it's important to know the system you are analyzing. I don't know what you do, you know. So you know which system is big. The important is to understand the impedance is not the only techniques. You can coupling with a DC, you can couple with other photochemistry, with other things. So don't think about only impedance. And careful of the data acquisition. If you made the wrong frequency range, you can take a lot of things wrong. Some reference. I always suggest some reference. This is the handbook from Alambard de Falkland. If you want to know more about the theory, you can download these two references from Solartron, are still 25 years old, but are still important to understand about impedance. The theory is not changing from 25 years old to now. Other two handbooks, this is the impedance from McDonald, and what I found very good as a reference is the Triboulet-Marcorazam for electrochemical impedance. The two guys are still around in all the meetings. Ross McDonald, I think there is retired totally, but Triboulet-Marcorazam, when you go to any congress, you met them, they are very friendly, and you can explain whatever and talk with them. They are very open-minded for chatting with you. You have our website. If you like, you can download anything you want from our website. And if you really want to suffer more, there is a nice theory about impedance again in our YouTube channel. You can go there and follow another 45 minutes about impedance theory if you not suffer enough today with me. Okay, thank you very much for your time and for your patience. It was difficult to make everything in very short time, but I managed. Questions?
There is one question.
Yes.
Can you say all the curves with the same shape have the same circuit?
No. So the same shape doesn't mean the same circuits. So again, like I said here, the equivalent circuits in this case, I can see the same shape, but can be totally different equivalent circuits. The important feature, I have to think what I have and response on my what I have on what can be my equivalent circuits.
I have a curiosity. Luca.
Yes.
Very often we take the specimen, we embed in a resin, and we expose this surface to the analysis.
Yes.
From your point of view, this is exactly the same system that just working on the surface, do the embedding. It's something, can you comment on the way you could analyze one of the 6 surfaces of a cube?
Depends to a lot on one problematic issues. On the frequency range you are working. So if you are working in, I always say the human frequency range on the level of, let's say the 1 millihertz, or let's say the 0.1 millihertz, then you are sure that you analyze only the open surface. But if you are going at microhertz, so microhertz, it means that I'm going at very low frequency, maybe you are able to analyze something that happened at microhertz, and probably at microhertz, you can probably read the other surface. Because you are going at very low frequency, you are catching something that is going later, and probably you are opening the system to going more and more and more at these sides, and probably to see what's going on at very low frequency. So let's say it in this way, your system probably is responding in something like this. But nobody said that after this there is something else. But in your system probably is finished here because you said, okay, my maximum frequency that I want to go is, let's say, the 0.1 millihertz. But what's going on if I go into 10 microhertz? Then maybe you take something else that is the semicircle from the resin. Of course, how much is the impedance of the resin? Probably is 100 gigaohm, so it's outside of the capacity of our system to measure. But it depends on the frequency range I'm using. You're welcome. It's clear for everyone, the question and the reply there? Clear. Any other question? Yes.
Is related to inductance.
Yes.
And it's not, it doesn't come from our system, it comes from there. So why we measure it, it comes from where exactly?
Thinking in this way, we always say that the first elements that we measure is between our working electrodes and our reference electrodes, okay? And is the resistance of a solution, correct? So is this point. It's real point because it's a resistance, so it's on the base, the basement that we have seen, the flat part, okay? Now, if you see something, what you did, you analyze this, or probably this to go to your potentiostat. So you start at the frequency range, at higher frequency range, that is not belongs to your system. So, as I said, if you have a reference electrodes, the maximum frequency you can is around 50 kilohertz. If you go at 1 megahertz, then probably you are analyze what's happened on your reference electrodes, what's happened on your cable, what's happened inside your potentiostat. Thinking in this way, it's a slow reaction. Going at a higher frequency, you do something very fast. How is working the reference electrodes? You have normally, you have here at bottom, you have a ceramic septum. Sometimes you have a glass when you're lucky, but the majority is the ceramic septum. The exchange between the solution inside and outside through a ceramic septum, slow. If you're going very fast above this frequency, you are measuring something else that is not belongs to your system. So, is an inductance. But remember that something can happen here. And this is important. Or something can happen here. So, and then is difference. Then is the problem. I will never worry about this. This one I'm happy when I see, because if I'm thinking about this one, how to analyze, then this one is painful. You're welcome. Any more questions, doubt, thinking? You can think about it. Me and myself and Eduardo, we are always available. So whenever you have a question and everything, you can send it to my email, you can send it to Eduardo, you can send it to our website. Say, hey, I see the presentation and I have a question. No problem. We are available to explain everything. And keep in mind that this presentation that we made, my watch doesn't work, but we made in around 1.5 hours. Normally, I'm doing in 1 day. So we were very fast on this presentation. So if you say, look, come again, because we did in Singapore many years ago, I was used to do this presentation every year because the student change. So every year they have a new students and they ask me to come every year to do the impedance presentation. So if you like, I'm opening to come here every year and do the same presentation. And, and there were people that they say, oh, but I saw you last year. No, but last year I was, now I prefer another one because it's important. So don't worry about it. Thank you very much again for your time. And as I said, I'm so glad to be again in contact with people after 18 months of stay at home and watching only the screen. Bye to the people online. And again, if you want me next time, I can come to visit your laboratory too. Thank you.